that brings us to the actual demo part that we ran. So we wanted to develop something for customer trainings that had a long length to diameter ratio and showed machining in linear segments, and show the following DIAEDGE and MOLDINO cutting tools, Citizen L32 capabilities, and ESPRIT CAM software. So this part will be broken up into 7 linear segments, and we'll talk quickly about the operations at each segment. So this is the first section that we'll talk about. We'll face the part. If we had any ID work that we wanted to do, we would go ahead and do that here before we rough turn the OD. This keeps the material in the guide bushing and keeps it rigid. So once we finish rough turning the OD, we'll come back and we'll finish turn it as well. ESPRIT has a really nice option in their contouring operation that allows for an edge break lead out, and that puts a nice chamfer on the OD as the tool pulls out. Then we'll come back and we're rotary milling the first portion of this thread, and we're milling a helical sweep with a VQ4 ball nose end mill, and we're using a rotary contouring operation, and this will be done in the first section and the second section so that we're still supported at the guide bushing for both of them. And Bruce is going to talk a little bit about the rough and finish turning inserts.
Okay, thanks, David. Real quickly, not to spend a lot of time on the tooling itself, but the SMG breaker is one that we've developed specifically for Swiss machining. So on these ground geometries here, 4th thou to a 16th thou nose radius, or a 0.1 to 0.4 millimeter, and a depth of cut up to about 80 thousandths, or 2 millimeters. It's a TICN coating that's been developed again for steel, but with added lubricity for, depending on the diameter of the parts, get pretty small, so sometimes our cutting speeds are relatively low compared to maybe some traditional types of application here. So that coating has been developed specifically for that. We also make them in our VP15 TF, which is our general purpose ALTIN type grade. This is for all materials, basically. It runs well in steel. It also runs well in stainless, cast iron, and the ISOS material groups, cobalt, chrome, zinc, and L, titanium, things like that. Quick word, the M in front of that SMG means that our nose radius, our corner radius on the insert is ground to a minus tolerance. And the reason we do that is to let that nose radius wear a little bit longer in between indexes. So, you know, without blowing out a radius tolerance if we have a tight tolerance on the part. The other breaker that we use in this particular demo is our LS breaker. Again, and this one is tailored more for the stainlesses and the ISOS, the high temperature type alloys here. So with that, we make this in our MP 9005, 9015 grades. This is a grade that we've developed especially for these high temperature alloys, these sticky materials, very good lubricity, but also it's an ALTIN coating, but we've added alumina to the coating to give it a little bit better heat resistance. So, you know, again, we're doing those difficult alloys.
Okay, so that brings us to our second section, and we'll pretty much do the same operations on the second section as we did the first. We have a rough turn of the OD using that MSMG breaker. Then we'll come back, we'll finish turn that with the LS breaker as well, and we'll add another one of those lead out chamfers on the bar. And then we'll come back and we'll rotary mill the second portion of that thread. So in a little ESPRIT tip, while we were programming this, I used the split face function. So that created a helical curve along that surface, and we used this curve as the driving feature for the rotary milling operation. And Bruce will talk a little more about the ball nose end mill.
Okay, thanks, David. Our VQ series end mills are especially made for these types of application areas: aerospace, medical, difficult to machine alloys is where they really shine. They work great in any material, but where they really work well is in some of these more difficult materials. So, and that's all a part of this aluminum chromium nitride coating. We call it our Smart Miracle. But something else about our small ball nose end mills here on the VQ series, it has a variable curve, which is on the cutting edge, flute to flute. We have the radius varies, between the two flutes. Again, this is all intended to break up the harmonics here. This also has a variable pitch. Depending on the size of the end mill, we will have a variable pitch. In other words, the spacing will differ flute to flute also. Again, this is all intended to break up any harmonics that we get.
So that brings us to our third section. And once again, we'll rough and finish turn that OD. And then we'll come over and we'll actually pick up with the sub spindle, and we're going to clamp on that diameter. Once we do that, we'll enter the G650 mode on the control, and that's going to actually allow us to use the sub spindle as a support. So then the rest of the part's going to be supported with the sub spindle, and you can see that coming over now. So the fourth section, still in G650 mode, rough finish turn that fourth section, and we're going to come over and we're going to rough and finish our OD grooves. The OD grooving is going to be done using a GTBH grooving tool holder with 3 different insert options. But Bruce will talk a little bit more about that in the next slide. And I think that tool's coming over right now. It's a little bit hard to see, but Bruce will tell us a little bit more about these.
Okay, the GTBH series of groovers. Again, this is strictly this is part of our small part machining program. These smaller shanks, smaller groove widths. We go down to 0.6 millimeters on a groove width. Actually, that's the depth. We actually get down to a 0.3 millimeter groove width. So all the way up to 3 millimeters. So, these are made, optimized for small part machining. You can kind of see here the different range of widths, depths, and then we make them also in 3 different edge preps, depending on the application. These are all made in that general purpose VP15 TF grade.
Okay, thank you, Bruce. That brings us to our 5th section, and we're going to rough finish turn that OD again. And then we're going to rechuck using the sub spindle so that we're a little bit closer up on the part and keep that part nice and rigid between your spindles and your guide bushing. So the rechuck operation for the sub spindles, just simply another pickup operation with your sub spindle, and you can see that there. So once we come to the section 6, we'll see that rechuck again with the sub spindle, finish turn that OD, and then we'll come in and we're going to drill 3 holes. We're using an MFE drill that we'll talk about some more in the next slide. It's drilling three entry holes. 2 of them are off center, and the 3rd one is on center. And we'll actually use that as a pilot hole or an entry hole for our VQ end mill. And then we'll see one of ESPRIT's profit milling operations in that pocket. So that's pretty cool to see that with the G650 mode. And it'll work its way out, rough and finish that pocket. And then we come back and we actually chamfer around that pocket once it's complete. So we'll go to the next slide, and Bruce will talk a little bit more about the MFE drill.
Okay, the MFE drill, we came out with that a couple, 3 years ago. It's a flat bottom point. So the reason we came out with this was to do those different types of applications, drill into an angle or a radius surface, create pilot holes for our standard solid carbide drills we have a point angle on them. So it's just a very versatile tool to do these kinds of operations. One application where it was particularly successful is for a customer of ours, Smith Titanium. They're running the MFE into the angled surface on a hex head on a bolt here. And they're drilling the cross holes for the safety wires for the race industry. And our VQ series, these are the square shoulder tools. We make them actually in several different configurations, but we'll talk here. And what we used on the demo was a 3-flute and a 4-flute. The 3-flute tool is, again, very versatile, lets us take a little bit more aggressive cuts with the one less flute, but we can also drill, we can plunge. It has one of the unique things about this, it has a variable helix between the 3 flutes. All 3 flutes have a different helix angle, again, to break up the harmonics. The 4-flute tool, the helix angles vary. They're 90 degrees to each other. So every other flute is going to have that variable helix also.
Okay, so that brings us to our last section on the main spindle, section number 7, and we're going to finish turn this diameter as well. And then we're going to come over and we're going to engrave a logo. So we're using a DLE 90-degree drill right there, and we're using that for engraving. We actually wrote another sub-program with a counter in it to cycle between the Mitsubishi Materials logo, CINCOM logo, and the ESPRIT logo. And then we're going to pre-part. We're actually pre-parting below our smallest milled feature. So what that does is that's given us a pre-parting so that we can avoid any interrupted cuts when we come back for the cutoff. Then we pre-drilled again, and then we can see another rechuck, getting up closer on the part. Then we're going to side mill the forks. So we'll do that on both sides. And then once this is complete, we'll come back using that same end mill and we'll plunge into those pre-drilled holes, and we'll work out using using a profit milling cycle in ESPRIT. So this is a pretty good view. Lets you see the sub spindle moving back and forth with the tool. So once the profit milling cycle is complete, then we'll cut off and transfer to the main spindle, or to the sub spindle, excuse me. And Bruce is going to talk a little bit about that GY grooving and cutoff insert that we pre-parted and then cut off with.
Thanks, David. The GY, this is our general purpose, more of a generally applied grooving cutoff type of system. We do make a specific design holder for the Swiss machines in these different seat sizes, which are going to tell us what groove width it is. Shanks are from 3/8 to 3/4 of an inch. And then we go 6 to 20 millimeters on the groove depth. So depending on and that depends on the width of the insert. Obviously, the bigger inserts we can go a little deeper with. The geometries that we have are the GU, GS, GM geometries. Those are our grooving and part-off geometries. And then the M geometries, those are going to be for multi-directional. So we can plunge, groove, then do side turning on these geometries as well. We have the ground geometry on our CBN. We make these with a CBN tip on them for hard turning. And then we also provide blanks. If you have a special form that you need for your operation, then we provide you with a blank that you can grind your own shape on the front of it. So again, carbide, cermet, and CBN grades, we make all 3 of those different tool materials in our Swiss GY system.
Okay. So after we cut off from the main spindle, we're over in the sub spindle, and we're going to finish up the part here on the sub spindle. So you can see the part coming over, and we're going to profit mill once again the fork all the way through. So we're actually using a rotary milling operation here. Usually these tools, you kind of start running out of Y travel when you're either on the top or the bottom of this tool post. So one way to get around that is using the rotary milling operation, and that's extremely easy to do within ESPRIT. So we can see here that we have a part, it's sticking out pretty far. We're only clamped up on about 1/4 inch, and then we have it hanging out another 1.5 inches or so. So that profit milling cycle allows us to keep our cutting forces low and helps us prevent from bending our workpiece or damaging our tools, because we have a pretty long engagement once we get to the bottom of that. So once again, easy to do within ESPRIT, and it gives you a workaround around running out of your or your y-axis travel. So once that pocket's finished, we'll come over to another DLE drill, and we're using this to cut a chamfer on all of those face features. So we're getting rid of all the sharp edges on the part. Generally, when you have a part come off the Swiss machine, you don't want to have to deburr it. So we're knocking all of our sharp edges off here. And then we'll come over to MOLDINO thread mill. This is an EDT thread mill. Once again, we run out of y-axis travel, so we're using our X, C, and Z axes together. And we're actually going to do this in 2 passes. So we have a rough and a finish pass. So that can allow us to control our diameter and minimize burring. If you were trying to do this right now with a threading boring bar, it'd be an interrupted cut. You'd lose a lot of tool life, and you'd have some pretty nasty burrs coming off. So that's the EDT thread mill. It is a center cutting thread mill. We also offer that as a non-center cutting thread mill. But you can pretty much thread something without having to pre-drill a hole, and that saves you a tool position in a Swiss machine. And then we can see the release and eject at the part chute using an M34 cycle. So that's the end of the part, and I just want to reiterate, so our goals at MTEC are to provide customer training and support, customer projects and application support, and we like to work with our partners such as ESPRIT and MCC to provide our customer base with the best possible solutions. Every training project, or every training and customer project at MTEC is an opportunity to establish a relationship with you, share knowledge, and earn your business.
Once again, thanks, David, and thanks for presenting that, and thanks for your time, everyone. And again, apologize for the live TV glitch here. So, but if you have any other questions regarding our tooling, our capabilities here at MTEC, you can reach out to either one of us or your local sales rep for Mitsubishi or DIAEDGE, and or your local distributor. Thanks.
So up next, we'll have Bud Felix from ESPRIT, and he'll be presenting.
Can everybody hear me? Okay.
Yeah,
that's great. Awesome. Okay, so hello, my name is Bud Felix. Today I'll be covering some super helpful programming techniques within ESPRIT. The primary topics of the discussion are programming for long parts and low frequency vibration on the Citizen L32. All right, so just putting a face to a name or a face to a voice here, better yet. All right, so firstly, we'll be covering the use of expressions within ESPRIT and how the programmer can easily automate sections of their ESPRIT file. We will then get into long part programming techniques for both segmented threading and rechucking with the subspindle. And lastly, we will implement LFV within ESPRIT. Expressions. So, expressions are an awesome way to have ESPRIT automatically run calculations within your operations. Today, we will demonstrate both the use of expressions and how to easily build them. So let's get going. So Swiss style programming is a very common practice to both face and turn the OD of your part in one sweeping move. So let's go ahead and simulate this and see what I'm talking about. All right, so you can see the cutter travels down the face of the part and along the OD. And I made this part extra long just for demonstration purposes. I'll speed this thing up, finish the operation, and let's take a quick look at the tool path. So you can see this pink racing stripe here comes down from the OD of the stock down to the center line of the part and then back up and along the OD. So in ESPRIT, we use an X offset lead-in to generate the facing portion of the cut. So looking at the operation settings, the lead-in type is set to Z and X offset. The X value is a pretty random number, so this is calculated using an expression. So if we open Edit Properties, we can see the expression has some weird values, some weird stuff, bar diameter, tool nose, radius, etc. So how is this made? Expression builder. So let's go ahead and build one. Clear this stuff out. All right. So the stock information for turning an ESPRIT is on the lathe machine setup. This is located in the ESPRIT objects folder. So I'll open this up for you and you can see lathe machine setup. If you double click on bar diameter, ESPRIT automatically drops in this code for you. However, the X offset lead-in value is a radial value, so we'll need to divide this bar diameter by 2, and that'll give us our stock radius. But if we stop here, the tool nose radius, if we stop here, the theoretical sharp corner of the turning insert would wrap into one nose radius below my stock OD, and that doesn't work. I don't want to crash my machine, so I want to add some clearance. So I'm going to do that now. And if you look down here on the left, you'll see tool 1, tool 2, tool 3. And for example, tool 1, let's say like you're doing a balanced roughing op, so tool 1 would be the leading tool, tool 2 would be the trailing tool, or if you're doing some milling, like a pocketing op, T1 would be my rougher, T2 would be my wall finish, T3 would be my floor finish. But we're just doing a contouring operation here, so tool 1 is all we need, it's the only thing at play. So we're going to cruise down, and we are going to find the tool nose radius option, and we'll double click on that, and you can see ESPRIT automatically drops in some code for us. All right, so if we stop the expression at this point, my tool nose radius would wrap in exactly to the OD of my stock. Again, not going to work. I do want to add a little bit of clearance. And then also, I would like to use this process or this operation down the line, maybe in another file, an inch file or a metric file. So what I want to use is I want to use a function that's built into ESPRIT's knowledge base that allows me to do exactly that. So again, I want to add a clearance value of either metric or inch. So I'm going to go ahead and add that. So again, we're adding a constant such that I can use this on either an inch or a metric file. So I type IM, inch or metric, open parentheses, and now I can drop in, say, an inch constant separated by a comma, and then I drop in my metric constant, close parentheses, press OK, and now I have my expression. So I'm going to go ahead and drop in 25 thou for this, and then an approximate metric equivalent, 0.5 millimeter. I'm going to close those parentheses, and I'm happy with this. This looks right. So I will press OK. All right, looks good. So I want to evaluate that expression, to confirm the syntax is good. So I'll debug this expression, and this will replace all the variables with numbers and calculate. And you can see the result is some crazy 0.3535. Either way, fine by me. I want ESPRIT to do the heavy lifting. I don't want to do these calculations, so I'll make ESPRIT do it for me. So let's quickly press OK, and then simulate. Make sure everything looks good. All right, no crash. Everything looks good. Okay, so let's really put this expression to work. Let's go to our machine setup. Let's take a look at our maximum diameter. Okay, so the machine will allow a little over 1.25 inches. So let's bump up my stock bar diameter to 1.25 inches. And that expression should go to work for me and update my tool path. There it goes. All right. So flexible files is what we're after. So expressions, major benefit. All right, segmented threading. Guide bushing support is the name of the game here. So if we were to process this part as if we were on a standard lathe, we would turn down the entire length of the part and begin threading. But for us, this would result in some pretty rough threads. So when creating long single point threads on a Swiss machine, it may be necessary to segment the thread into multiple sections. Of course, in this case, we definitely need to do so. Also, a couple more notes before we get started. When segmenting a long threaded area, it is typical to overlap at least one thread pitch between thread segments, as well as starting and ending each thread pass with an angled lead in and lead out. So if we follow these two guidelines, our threads will be seamless. So let's get into it. All right. So in this example, we're going to do a quarter 20 thread that spans about 1.5 inches. So I want to segment this guy. I want to break it up into 3 half-inch chunks. But the first thing I want to do is I want to pull some geometry from this model. I want to make a few chains. So the first chain I want to do a face and OD turning up, just like in the previous example. I want to make a thread chain, and I also want to make an OD turn chain for the segment right after the first threaded section. So first things first, I'm going to do an intersection point at the leading edge of my part. And again, I want to break this up into half-inch sections, so I'm going to drop another point along the OD of the part. And I also want to add 3 times the pitch here. So I'm going to do 0.15 plus 0.5. So our pitch is 0.05 times 3, 0.15 plus 0.5, 650. Okay, sorry, a lot of math. Got to keep cruising. So now we're working on our threaded chain. Again, we're going to use an angled lead in, lead out. And so to make this easy on myself, the change in Z for the lead in, lead out is a multiple of the pitch. So in this case, 50 thou. So a Z change of 50 thou will be used here. So again, I'm just dropping points here so I can create my chain. You could definitely do a manual chain here, but it's personal preference for me. I really like the auto chain command. Super simple. I like it a lot, so I went ahead and just used that. So the next thing I want to do, I want to make my OD turn segment right after the first thread. So what I'm going to do is I'm just going to copy and translate that segment that we just made by a half-inch, and there you have it. So let's make some chains. We have our geometry. Let's make some chains. So face and OD turn. Go ahead and highlight what I need. Select auto chain. Boom. Got our first chain down. Next thing I want to do is I want to make my thread chain. Highlight and auto chain. All right, we're looking good. And then lastly, I want to auto chain the OD2 turn. So, all right, we look good. So let's go ahead and let's add a process to the first chain. So the face and OD. So again, I want to reuse processes. I want to save time. I've already got this process made up. Super duper simple to make. You guys just saw me make this. There's our tool path right there. So let's go ahead and turn on our stock. And let's see what that cut represents. There it is. All right, we're looking good so far. So now I want to go ahead and do the same thing. I want to add a quarter 20 process. I do have one of these process saved. ESPRIT makes it super duper easy on you. If you wanted to go ahead and add a thread, if you didn't have the information already locked and loaded, ESPRIT ships with a database. So I'll jump down to the thread tab. And you will see here from database, click my wand, and we already have just a ton of data. So you see nominal diameter, lead, major diameter. So if I select one of these guys, these are recommendations, it populates these fields automatically, but I've already got my quarter 20 and we need to keep cruising. So let's go ahead and simulate, make sure this looks good, make sure I'm not crashing my machine. So again, face, pull back, turn the OD, chamfer lead out, and let's go ahead and thread this guy. All right, and again, maintaining guide bushing support. I want to make sure that I'm not drawing back too far. We're turning in half-inch segments, so we're pretty safe here. All right, so let's continue. So the next thing I want to do a contouring op. I just want to turn down this next section such that I can begin my next round of threading. All right, simulate this really quick, run through it fast. Turn, thread, followed by another turn to set up for our next threading section with a chamfer lead out to protect my guide bushing. and we're good to go. All right, so just like I copied and translated that segment for my second OD turn section, I'm going to highlight these operations, right-click copy, and I'm going to translate by a ½ inch. I want to make 2 more copies to then span my total 1.5 inches. So change that to a 2, translate an X, 0.5 inches, press OK, stock updates, there we have it. So we have successfully done segmented threading. So let's go ahead and watch a simulation to make sure everything checks out. So turn, chamfer lead out, thread, turn again, same deal. Guide bushing looks good. We're not drawing back too far. Turning down for our last segmented thread section. And there it is. Looks good. Okay, guys, I know that was fast, but gotta keep cruising. All right, so next thing we're gonna be doing is rechucking with the sub spindle. We're gonna show you how to lay that out with respect to the operations and also sinks. So let's get going here. All right, so just to make sure we're all on the same page, rechucking with the sub spindle, I'm gonna go ahead and simulate this. I've already got it pre-programmed. Again, I made this part extra long because I really wanted to show off. Like, you can see the main spindle sneaking up on the guide bushing housing. Sub spindle comes forward, grabs the part, commence the rechucking, and then we do some more work. So turn, some grooving, followed by a little bit more turning. Perfect. Okay. So I want to go ahead and I want to put ESPRIT through the ringer really quick. I want to see what it does. So this part's super duper long, and if I didn't rechuck, how would ESPRIT handle that? So I want to go ahead and remove these sinks. I want to get rid of my rechuck operation. I want to get rid of this G600. I want to get rid of my pickup. So now I've got this super long part. I have no rechucking operation. Let's just see how this is handled. So everything looks the same so far. Main spindle get in pretty close to my guide bushing housing. And there we go. All right, so I just crashed my machine. No problem here though, we're in ESPRIT. So let's go ahead and let's add these operations. Let's go ahead and do a rechucking operation. So this is comprised really of 2 operations. You want to first do a pickup. And I went ahead and I set a pickup position 4 inches from the leading edge of my part. So I'm going to go ahead and hide the solid here, and you will see the geometry, a little point here. I'm going to select my cursor, and boom, those values will automatically populate within those position fields. Again, I want ESPRIT to do the heavy lifting for me, so I went ahead and made an expression for the clearance value. I want to be 100 thou in front of the leading edge of my part, so I did the absolute value of some tech object 427 plus my really awesome function inch metric 100 thou or 2 millimeters. So I'm going to cancel that out, and I show you right here that this is tech object 427 or CL file 427. So we're just referencing this field to then do some math on. So like in my clearance image. Okay, so again, I want to reiterate, a tech object is essentially, it's just a variable name or a keyword used for when the user wants to reference a variable within the same operation. So again, 427 is the Z variable in position. So I'm happy with this. I'm going to select OK. Awesome. So if I highlight this operation, we can go ahead and see that our operation begins 100 thou in front of our part. So we're going to wrap it up to that point, and then we will feed all the way up to our 4 inches beyond the leading edge of our part. So moving on, we've got to add a bar feeding operation. So bar feed by spindle, spindle name main spindle, because this is the spindle that is actually opening up and moving back. And then bar spindle name is sub spindle because this is the one actually holding the part. And also this rechucking value, we will be essentially bar feeding at that stated value. Let's move on to the bar feed tab. Awesome. So, okay, just like the pickup position, we have the same fields laid out. It is very important, in fact, it's 100% necessary that this position Z is equal to the pickup position Z value. And then also our feed length and reposition distance is how much you want the main spindle to back up. So this will actually output a G50W shift, which will let the machine know that 0 has moved. So you won't have some funky value like part length plus whatever this is. So in this case, 4 inches. All right, so we're not out of the weeds quite yet. We have both of our operations. We need to reorganize them. So in ESPRIT, it's super duper easy. Just a quick drag and drop. I move my rechuck behind my face and OD turn. Again, though, we're not completely done. We need to synchronize these heads. Syncing in ESPRIT, super easy. So select the operation, a simple click and drag motion. So we drag from head 1 over to head 2. Same thing, click the operation, drag, place, head 2. All right, so face and OD or turn operation will complete, pickup will come in, that will complete, and then the rechuck will start. So we read top down, everything looks good to me, so let's go ahead and let's simulate. Face and OD, main spindle coming forward, and sub spindle, rechuck our 4 inches, and continue doing your work. Very good. All right, so sync strings, substrings, and how to manage them. So the post manual, this is an awesome portion of the ESPRIT package. So not only do you get a factory certified post processor and machine setup that is a true digital twin of your machining environment, but you also get a manual to help you set up your program and generate the output you are looking for. And I say the output you are looking for because these machines are incredibly complex and configurable in a multitude of ways. Now, I really haven't been doing this for that long, but it's seemingly very rare that 2 machine shops run the same machine in the exact same way. So, running down to the first page, the revision sheet. So you can see that this post processor has been in the field since 2015. So that means this thing has been put through the ringer for 5 years. I mean, the L32 is a relatively young machine, but ESPRIT and Citizen have had a long-standing relationship for nearly 2 decades. ESPRIT has more than 90% of Citizen's product line covered from current to machines of the mid-90s. The post manual offers incredibly detailed descriptions, both through text and images. Right now, we have a super well laid out table of contents, information. So set work system, machining length, T-code arguments, tool offsets, synchronization codes, supporting long parts. So sync codes is what we want. So we go ahead and click on that, and the document jumps straight to sync codes. So G610, G620, Z1, Z2 superimposition, full description. Truly is a fantastic guide and a fantastic training manual. Super, just right here. So we have our operations page. Oh, no, we'll skip through to the next. We are running low on time. So let's go ahead and throw some syncs in. So just like Dave's file, he needed a G650 to superimpose Z2 onto Z1. And it's super easy to do this in ESPRIT. You just double click on the sync and then you drop down to your machine specific G codes. Okay, so we're not quite done. We still need subsyncs. We need to add a W0. So the default machine behavior when say like a G600 or a G650 is enabled, the sub spindle actually wants to go home. So these subsyncs, or these substrings better yet, tell the machine, hey, we want the sub spindle to stay right there. And this is good for us because we just brought the sub spindle forward. We don't want it going anywhere. And we definitely don't want it following the main spindle during its rechuck. So quickly, again, adding a sync, G650, turn 650 back on, add a W0. And then another kind of cool thing, if you want to make a comment or maybe a note to your operator, you can write in parentheses, and this will output in your NC file. So, hey, what is this G600 for? Oh, so we're waiting for rechuck. Just another form of communication, super simple to do, super handy. All right, last but very not least, so we have low frequency vibration. We have two modes, so let's jump into this. So quickly, post manual, super dynamic document here. I can use Control F, punch in LFV, and boom, it cycles right to the first LFV that it finds. So I want to keep cruising. There it is, low frequency vibration, G165. So this is all handled in your operations custom settings. So again, we have two modes to work with here. This is toggled through custom setting 7. Let's get into it. So on turn OD2, let's go ahead and enable mode 1. So I'm going to go ahead and open up this operation. And I'm going to cruise down to the custom settings tab. And I do want to enable mode 1. So mode 1 is multiple oscillations per spindle revolution. And custom setting 8, Q amplifeed over feed ratio, punch in a value for this. Custom setting 9, variable D, number of oscillations per spindle revolution, punch in a value, press OK. And let's go ahead and check the result of this. So I'm going to go ahead and post code, just select that operation, post out the code just for this operation. And if we squint our eyes just a little bit, you'll see on line 28, you can see G165, P1, Q1, D2. So there it is. We just posted out or proved that we have enabled LFV. Super duper simple to do right there in the custom settings. All right, guys. So again, thank you very much. Just a quick summary. Long part programming, we covered quickly, segmented threading, rechucking with the sub, turning the LFV, and then expressions, so automating your processes. So again, I'm Bud Felix with ESPRIT. I want to thank both Citizen and Mitsubishi. We appreciate your time. Thank you, guys. Thank you so much.
Hey, Tim, you're still muted right now, just to give you a heads up.
Good morning. My name is Tim Duffy of Marubeni Citizen-CINCOM. Today I will be giving a brief review of low frequency vibration. I will also be reviewing some of the automation packages that we have developed for our CINCOM machines, along with a review of some of the engineered accessories. Low frequency vibration, or LFV. In low frequency vibration cutting, a servo-controlled axis generates vibration behavior in the axial direction. Machining is carried out while synchronizing this vibration with spindle rotation. This creates air cutting time during machining and leads to intermittent chip disposal. The diagram below shows two cutting paths through two revolutions of the main spindle. The light blue area is showing the cutting area of the first revolution. The darker blue area shows the cutting area during the second revolution. So these two cutting paths are overlapped. This video graphic shows the cutting paths as described in the previous slide. oscillation that is synchronized with the rotation of the spindle. It is also phased with spindle rotation. Here we are seeing the oscillation during cutting, which breaks the chip. This leaves a corrugated surface after the first pass. On the second pass, the high spots are removed. So in between we have an air cut, which breaks up the chip. As mentioned, the oscillation of the axis is fully synchronized with the main spindle. So on the second pass, we take off the high spots from the first pass. The last cut at the end of the treble, the vibration stops, and this creates or forms a flat surface up to a shoulder. We also have LFV available in the radial direction. Here we're seeing the LFV being used to cut a groove. So it feeds in, backs out the cut, breaks the chip. And in this case, on the second revolution, it removes the high spots from the first pass. What materials would benefit from this LFV technology? LFV certainly has its advantages in stringy materials, Inconels, stainless steels, copper, pure iron, plastics. The chips on the right are from conventional cutting. As you can see, they're long, they're stringy. The chips from LFV cutting on the left are small and compact. Both sets of chips are the same weight. It's the same volume of material. Here we see the machining of a nylon part on an L20 machine. On a normal cutting in this material, we'd expect a long, stringy chip that could wrap around the part. In this video clip, the chip is short and manageable, eliminating the possibility of chip wrap. In this video, we are turning nickel silver, once again on an L20. The right side shows the difference using LFV. On the left side, chips get wrapped around the part. This creates a problem when picking off. Now, chips on the part, picking off a part. This results in damaged parts or chucking alarms. This part is grooved, which doesn't help as far as the chips getting hung up in the grooves. Now you're seeing the sub-spindle approach. They're saying make a right mess with the bird's nest on the left-hand side. Let's look at the benefits of low-frequency vibration. It's ideal for difficult to cut materials. Reduces downtime, i.e. chip wrap, chucking alarms. Therefore, it increases the productivity and the profit. Efficient through a combination of vibration and standard cutting. So we can turn LFV on when we need it, we can turn it off when we don't need it. It's excellent for deep hole drilling. It's easy programmable chip control. Chips are broken up and do not become entangled with the material or the tool. The cutting resistance is lowered. Reduction or removes the need for high pressure coolant. No build-up edges on tools. The machining temperature doesn't rise, so less thermal distortion is expected. Here we see what LFV can do when cutting 17-4 stainless. We have a very controlled chip in the bag on the right. There are 3 operation modes in LFV. We have mode 1, and this is mode 1 is the multiple oscillations per revolution, where the feed axis oscillates multiple times during one revolution. In the animations we showed you earlier, that was LFV mode 1. On one revolution, it oscillated 2 times. Mode 2, this is multiple revolutions per oscillation. So we might say go 20 revolutions and then oscillate once in this mode. This is where the spindle rotates multiple revolutions during one oscillation of the feed axis. We have recently reduced LFV mode 3. This is the threading mode. The x-axis oscillates for each threading pass. So as it's feeding down the helix of the thread, the x-axis is backing off, in other words, breaking the chip. This requires 2 cutting passes for each normal pass. So we feed down once, we're backing off. The second pass, it takes the high spots off. And the last path is normal LFV. So the threading cycle actually takes a longer time than it would normally. But as I say, you're not getting any stringy chips wrapping around on ID threading tools especially. What applications can each mode offer? LFV mode 1, the machining of difficult to cut materials. We can groove, we can drill, we can cut off. LFV mode 2, machining with small drills, smaller diameter materials where high surface feet per minute is required. There's limitations on how fast we can go with the spindle as far as each of these modes. If we're going at 6,000 RPM and we're oscillating using LFV mode 1 2 or 3 times during the cut, the machine wouldn't be allowed to do 6,000. There's limits on what we can do with that mode. On LFV mode 2, you probably can go at a higher surface footage because you're going X amount of revolutions per oscillation. On LFV mode 3, obviously, it's threading cycles. It's easy programmable. It's basically one special G code that turns LFV on and creates the cutting parameters. Subsequent code is standard cutting code, G1s, G2s, etc. The LFV function is available on various CINCOM models, latest generation models I should mention. So if you've got a machine that's 20 years old, unfortunately we can't install LFV on that machine. These LFV machines are LFV ready machines, are specially built. They've got upgraded bolt screws, slideways are improved. As well as CINCOM models, LFV is also available on the Miyano BNA 42 GTY. However, the GTY is only available as a special order machine. The following automation has been developed from the needs of our customers by our New England-based R&D department. We're going to look at a wire ejector, the basic system, and we're going to look at a system with a full tray automation. We're going to look at a vacuum ejector, a basic system with a parts carousel, then a system with a full tray automation. And we're going to look at a gripper unloader, a basic unloader, a gripper unloader with a parts carousel, and a gripper unloader with full automation. The wire ejector. Traditionally long parts which cannot be ejected through the normally ejection process via the standard parts bin are extracted through the sub-spindle or pick-off spindle. The regular long workpiece device concept is to insert a liner inside the subspindle that allows us to push the previous machined part in the subspindle with the next part until the parts finally fall out the back end of the subspindle. This works well, however, it can be the cause of jams in the discharge tube, depending on part profiles. In addition, this process does not allow for sharp tips on the end face of the parts. So the solution for these parts, or these types of parts, long parts, is a wire ejector. The wire ejector pushes the part through the subspindle collet and the discharge tube until the part is completely ejected. The video on the right shows a part in the subspindle being pushed by the ejection wire. The left side shows the back end of the subspindle with the spindle liner installed to accommodate the long part. The long workpiece tray is also attached to catch the parts. However, it's not shown in the video. So we can look at that video of the wire on the right. It's just pushed the part through. The wire is just retracted back. And the video on the left is showing you the part getting pushed out the rear end of the subspindle. There are two types of wire ejection units. We have a pneumatic type and a servo type. Both are mounted on the side of the bar loader. The servo type allows us to change the speed of the push-out and the push-out position. You can also detect if there's a fault with the part getting jammed during the extraction. So the video on the upper left is just showing you the servo feeding the wire forward. Slight dwell, and it's going to feed the wire back. So with that motion, it's just pushed the part through the subspindle. Here's a wire ejection unit that has been fully adapted to an automated tray system. So it pushes the parts out. There's actually two sets of trays in this system that we installed. There's a redundant tray sitting waiting. When the first tray gets full, it will replace the tray. So it's taken the empty tray and loaded it on the top shelf, and then it's taken the full tray and brought it back where the operator can go in and pull the tray out of parts. The vacuum ejector. Many medical parts are so tiny and very difficult to eject by a regular ejector on the subspindle. Many customers complain that parts get lost in the system. The vacuum ejector collects small parts in an airstream. Strong negative air generator can catch the parts, and a plastic deceleration funnel prevents damage to these parts. The vacuum ejector can be used as a single bin system, or we can add a parts carousel that can help when trying to inspect large volumes of parts. The part is extracted from the subspindle, then into a funnel that helps to gradually slow down the part so it does not get damaged. So it sucks the part out into the funnel, and then it slows down. Here we see the vacuum extraction unit in combination with a full tray automation unit. So the subspindle positions at a location and spits the part out. You can see a little red dot. Part travels through the tube into the funnel, so it spins around and spirals down the funnel. And here it's getting dropped into a fully automated tray system. Replacing the tray with an empty. So within this system, and any time during the process, we can hit a button and it's really going to drop the next part off in a little chute so this part can be inspected. There's nothing worse than having a a bin full of 200 small parts like that, and then picking one out and finding that that particular part is out of spec. Now you've got to inspect all 200 parts or whatever the case may be. The following tooling and accessories have been developed from the needs of our customers by our New England-based R&D department. We've got B-axis modular tooling, thread whirling units for bone screw applications, 80,000 RPM electric high-speed spindles, bobbin spindles, back slit and saw spindles, tandem spindles that give us more live tools for the back, stationary tool blocks, reduction chuck sleeves, overgrip kits, and rotary parts carousels. The standard B-axis tooling on the L20 and L32 machines has 4 front live and 4 back live positions. They are built-in spindles with ER11 style collets. So that's what you're looking at now. You can do obviously various operations with these: angular drilling, helical milling, angular OD threading, and 4-axis simultaneous milling. So that's the standard B-axis unit. So to have a more flexible type system, we developed a modular B-axis unit. So here we see on the right the modular unit. It's available for the L220 and the L32, obviously the type 12 with the B-axis. Showing you the modular unit. Here it is with 3 regular spindles, AR16. We can put high-speed spindles in there. We can put double cross spindles to give us more live. We can put triple face front and back. We can put thread whirlers in this modular unit. So it's given us a lot more flexibility. Thread whirling. Bone screws are complex threaded components, usually requiring numerous hours of process development, setup, debugging, and cycle time. Thread whirling is the most efficient means to produce difficult OD threads by providing a solution that minimizes development to production time with faster cycles. Flexibility of thread whirling enables cost reductions with setup simplifications, faster cycles, and greater throughput. High-speed spindle systems that are air-cooled are an ideal add-on for very small parts. 4 different units are listed here, all with a max spindle speed of 80,000 RPM. The speed can be controlled in 1,000 RPM increments and is controlled via the program by B codes. Here are various configurations of high-speed spindles installed on a K16 machine. We have back cross working on the upper left. We have angular working on the front side in the upper right. We have angular working on the back side on the lower left. And on the front end, face working on the lower right. High-speed spindles are being installed on L12 Type 7 machines by using special ID tool blocks. On the left, here's a special block for 3 high-speed spindles in a cross-working location. The right shows 4 high-speed spindles for front-end face working. Slit and saw attachment for use on the sub-spindle on an L32 has been developed that can handle a 2-inch diameter cutter. It has a 3/5 reduction ratio that increased the usable torque. Bobbin spindles have been developed for the L20 and L32 machines. The one here is to be used with an arbor in an ER20 collet. The arbor is supported at both ends. The max helix with this unit is 2 degrees. This is the 2nd generation bobbin spindle that uses a solid one piece over. This unit allows up to 45 degrees of helix. When you need more live face tools on the L20 or L32 machines, we have a tandem end face spindle that will give us a live tool in both the upper and lower tool positions of the back tool post. A 4-position stationary tool block has been developed for the new L220 Type 10 machine. So the L220 Type 10 is the Y-axis on the sub-spindle, so we can have 2 levels of tools. Here we see a deep drilling block that is mounted on the gang on an L12 Type 7 machine. The drilling depth has been increased by another 2.3 inches. Main and sub-spindle kits for increasing or decreasing chucking capacity have been developed. A large TF37 collet that is standard on a 32mm machine can be adapted to take small TF15 style collets that will help when machining small parts. Overgrip collet kits are available with up to 3mm of overgrip. This is needed on many bone screw applications today. Harding spec overgrip collets are available with a maximum of 2.2 of overgrip on a TF25 size collet. With the overgrip kit, this can be increased to 3mm. Rotary parts carousels are available in 3 types. There's a standalone version. There's a version mounted on the side of the machine, shown here with a vacuum ejector. The 3rd version is a swing mount that allows access to the chip pan when swung away from the machine. That concludes the MCC portion of the presentation for today. If you need further information on any of the products discussed, please contact your local distributor. Thank you for your attention.
From this guy.
We're on yours, actually. I'll just go. All right, everyone. Thanks again for joining us, and thanks for sticking with us through our technical glitch there. And I hopefully you've got something out of the presentation today. It's contact information for all 3 of the different companies here. David or I for Mitsubishi Materials, Cash, Bud Felix, or Dan Perry for ESPRIT DP Technology, and then certainly you can contact anybody, your local citizen dealer. Here in the Carolinas, it's a depth machine tool, but there are other, I guess, distributors throughout the country. So, or you can just contact Marubeni Citizen-CINCOM directly. Sure, Tim will be able to answer any questions you have. So, thanks again, and please, let us know if you have any questions or if you need any other information. Appreciate you coming.
Thanks, guys.